Alright, have the video on for a little bit. We have company today, and fortunately I can get to my keyboard and the mouse. So if a big tail pops up in the video at some point, it's this guy's. But he's out like a light. And we've been having difficulty all morning with network. So I have two classes right before this one, and had a stall of the Zoom call. Was able to reestablish connection after a few minutes. So just be aware that could happen to y'all on this one. I've got the recorder running right now, I believe. Let me check that. It's running, so we'll be able to have a recording. And as everyone's connecting, I want to call your attention to the quiz collection category. A few of them miraculously appeared yesterday. And so your next one, quiz 3 and 4, are both due next Monday. So there's plenty of time to complete them, and they're not terribly difficult. Oh, you can see there's a few others upcoming. They've not been activated yet. So for the time being, don't worry about them, and I will adhere to when I post a quiz, there'll be at least 1 week till it has to be completed, which should give plenty of time and at least one class meeting before it's due. So I'm relying heavily on these in hopes that I can keep our examinations quite a bit simpler. So the quizzes aren't meant to be hard, but you might get a question or two wrong, and when you look at the answers, I hope that will you'll indicate and see why. Usually it's a misreading or misunderstanding my intent. Let's see if the back version works. We have 29 people. And let me check lesson collection. Today is lesson 7. Okay, that's active. Good.
Look at the help section in your Alexa app.
And so you can tell by the speed of anything going on that nothing's working well today. So of all days to have the network not work well, this is actually a good one, because this is a look at storage concepts in water supply. In the data links section, there is a spreadsheet, and we will at least look at output from that in a little bit. And there's supplemental data which has an example, and we'll work through that in a little bit. Video links, there's the 2019 version of this lecture. So they're there. Let me check that the links are active. This should come up with YouTube, possibly in my lifetime. Okay, good. That link is active, and the 2019 storage concept is active. These two, today's lessons, obviously aren't posted yet because they don't exist yet, and we're making them as we go. The lesson description is storage principles for service, fire, and emergency storage components. A little picture show of different kinds of storage tanks, and then example calculations for flow equalization storage, which is one of the calculations that one would do in storage design. Probably the most useful reading would be the water distribution systems in the land development handbook. The other ones are more focused on the hydraulics of flow, and there's not much detail on storage. Actually, although there is a good reading on storage in the reading list in WORBS. See if I can find it. I think it's that one. Let's find out. Yeah, so WORBS 130 to 198 has a useful section on storage that I'm scrolling down to as everyone's logging in. Possibly you're getting nauseous. That means I'm scrolling fast enough. Remember, if you get nauseous in my lectures, all you have to do is close your eyes and stop listening, and you'll be better in an instant. And we'll actually revisit this lecture in more detail starting Thursday when we start getting into network analysis. I'm pretty sure he has a whole section on storage tanks. Ooh, fans of my computer are coming on big time. So, yeah, we're getting there. There we go. He's got some discussion on storage, equalization, and fire, and so on. So that's a good reading. I will try to modify the cover page to directly go to that reading. And so now we'll begin with our actual lesson notes. I'm going to mute everybody. Hopefully it doesn't mute me. So if you have a question, you can unmute yourself and ask the question, and I'll leave a little bit of the chat open over here. Let me do some more real estate work on the screen. This is the hardest part of doing these Zoom calls, or even if I use Blackboard Collaborate, same thing. Trying to maximize the use of the screen real estate so that everything gets recorded. I think I'm set up, good to go now, so let's begin. So this lesson, again, like seemingly all the other ones, I'll talk a lot and go through the various materials that you can check out on your own later. But this is primarily aimed at drinking water storage. Many of the concepts would be applicable to the other two types of water systems we're concerned with, which would be stormwater and wastewater. We certainly don't usually store wastewater in elevated storage tanks. Just the thought of that breaking is grotesque. Same with stormwater. We don't want to invest the energy cost to raise stormwater up into the air. Nevertheless, the two are still stored in many instances for treatment and ultimate return to the environment. And many of the principles here apply, bearing in mind that we're not going to put them up in the air. So storage is used in water supply, stormwater management, and wastewater systems for a variety of reasons, and a few of them are listed here. Service storage is the primary use of storage on the drinking water supply side, and it's used for a property called flow equalization. Generally, things are designed for some particular steady flow rate, and storage is used to accommodate variable flow rates in the system. Secondary use of service storage is for pressure zone maintenance. Emergency storage is storage that's kept around to supply water during a repair or some other system failure. Fire storage is used to provide supply during firefighting activities, and you could logically consider it part of emergency, but usually you consider it separately. So Yuan's exercise, how is fire flow determined in exercise 3? In the design manual for San Marcos, there's a stated flow rate for a fire hydrant, and somewhere else in the design manual it should tell the spacing of the fire hydrant, so every 200 feet or something. And so the combination of those two pieces of information is how fire flow would be determined in exercise 3. Storage is either elevated, it's above ground, up in the air, at grade, on the ground or in the ground, and below grade, which is subsurface vaults, not to be confused with aquifers. So subsurface vault and an aquifer are not the same thing, and it's pretty uncommon to confuse the two, but it's possible. So surface reservoirs are used where natural elevation is high enough, and it provides us a way to use inexpensive pump storage. The reservoirs themselves are covered for their protection to prevent contamination, algae growth, evaporation. Out there on the West Coast, a few years back, the city of Portland, Oregon, they seem to be making the news a lot lately, had some high school youth that contributed a bladder full of unacceptable water to a drinking water reservoir. And rather than just chlorinate the crap out of it, the city wasted hundreds of thousands of gallons of water from the reservoir to return it back to its usable condition. And that's an example of where a cyclone fence might have prevented them from having to waste that water. I'm certain they're always young men. I'm certain the young men had consequences for that, other than getting laughed at. Hopefully for their families, the city didn't charge them the retail cost of that water that had to be replaced. For what it's worth, from a public health standpoint, there's no risk. I'm not encouraging you all to go urinate in reservoirs. That's generally a bad idea. But there's so much dilution, there's pretty much no chance of pathogen coming out of you getting into the rest of the system, especially since the water is going to go through treatment. So here's a diagram of what's meant by elevated storage. There's a reservoir up here, in this case on the side of a hill, and we want to serve down here. We have that much operating head or energy totally contributed by the pool elevation in the reservoir. So that's great, except here in Lubbock, where we don't have a whole lot of hills conveniently nearby. A second technology is called a standpipe, and these are, in their very essence, vertical cylindrical pipes, or usually cylinders, where the height is greater than the diameter, and it's filled with water. And there's a pool elevation shown up here at the top. There is a portion that's called useful storage, and then there's a portion called the supporting storage. The supporting storage, it's defined by the minimum desired pressure head that we want to have in the system, and then any storage above that is the useful storage. So that's the volume above the elevation needed for minimum pressure, and the minimum desired pressure of the supporting storage can be employed in an emergency. These are usually made out of steel, reinforced concrete. I've driven through Texas and seen some that appear to be a fiber reinforced polymer, like a fiberglass, but I'm not sure. I didn't get out of the car and jump a fence and go bang on them to find that out. It's quite possible that the fiberglass was just an exterior coating. It has to be able to support the pressure down here at the bottom. So, if there's 100 feet of water, that's nearly 3 atmospheres. So that's going to be 45 psi at the bottom. But when you multiply by the area, that's a substantial amount of force. So there'd be some reinforcing at the bottom. But other than that pressure force, most of the weight is supported by the foundation on the ground. So here's some photographs of elevated tanks. These are not standpipes. These are tanks that are held up in the air. So here's an elliptical shaped one, and then here's the supporting structure. And the supporting structure doesn't have water all in it. There's a pipe in there, and then a framework structure to hold this up in the air. And then when the alien mothership returns, this one can be activated, and it comes off this supporting structure, and it's already halfway to space. And then here's another one, a similar structural design, much larger column diameter, and then yet another one shown here. These are all quite similar morphologically, and you can see that they've leveraged them for their main purpose, which isn't to hold water, but to be able to paint some icon of the community on them, usually the high school football team. A second design related to those is called the Hydro Pillar, and this is a brand. And in these pillars, they've actually incorporated utility shops down in the bottom and in the waters up top. In earthquake country, I personally wouldn't want to live and work in this thing because I know how earthquakes are, and that thing would come and squash me. And then here's one with supported buttresses, again to hold the tank up in the air. More hydro pillars, and bearing in mind they have the ability to, again, show the name of the high school football team. This one, Jefferson County, Alabama. That's kind of interesting because you can only see that from the air. So as you are landing your small aircraft, you get to know where you are. And then here's another one with a name of the community. This one here on the left is interesting because it also has a clock on it. And if we look up to some other examples, here's a clock. So in these particular communities, in homage to the Rolling Stones, time is on their side. So they provide clocks so you know where it is. A second morphology are called water spheroids. And these, again, the same basic design is there's a connection from the surface to the tank, providing the mechanical support as well as the infrastructure to bring water in and out of the tank, and then a spherical shape on top. And these have some utility compared to the hydro pillars. They can't get as big because of the structural requirements, because in addition to having to resist vertical forces, there's clearly going to be wind forces. So these are on slender columns, and if you remember from your structures class, there's issues with slender columns to be sure they don't have too much lateral force and bend over and crash and go boom. These have the advantage that they can be disguised to look like other things. So here's one that's disguised as a peach. So if you're driving through this community and you see a big peach in the air, it's like, whoa, they got big peaches here. And you wouldn't know it's a water tank. Of course you'd know it's a water tank. Again, there's an aesthetic conferred by being able to disguise the tank to some unique feature. So undoubtedly in this particular community here, whether it's disguised as a peach, they probably grow and export peaches, and or it's in Atlanta, I don't know which. They grow and export peaches, and so they use the tower again as advertising for the community. But it's the same basic thing. It's a big tank up in the air. And then moving to ground level tanks, we're all familiar with these, I would think. So here's large tanks that have a large diameter, relatively low height compared to the diameter, and then here's a standpipe. So the diameter is smaller than the height. Ground level tank, the diameter is bigger than the height. And this might be 50 or 60 feet high, but it's hundreds of feet in diameter. So these have the advantage that they can actually scale pretty easily. So if you need more water, you just make a bigger tank. They still have to manage pressure at the bottom, but not as much as in a standpipe. And they may have booster pumps to boost pressure to get them into the system. Some more pictures of standpipes and reservoirs. Reservoir, standpipe. So the ground tanks are often called reservoirs. And then within many of these, when you specify one or if you're designing one, your various vendors, so there's a couple of companies throughout the United States that earn much of their living by designing and installing such tanks. One is called, this is a fresh mix mixing system, and the purpose of that is to keep the water inside the standpipe fresh, in the sense that there's no stagnant zones. Because if it's treated water and it's put in there with disinfection residual, after a few days that residual is gone and the water could becomes no longer microbiologically safe. But by mixing it, it can be maintained as uniformly treated for longer periods of time. So this one's using a draft tube mixer, and there's an external, there would probably be an external power source to create the mixing, like a pump, if you will. Or they could possibly do convective mixing by using thermal forces to make that happen. That wouldn't take any power, but I think it would be extremely hard to verify that it's functioning properly. So here's some pictures of composite elevated tanks. And so this is a elevated tank as well as a fairly large diameter standpipe. And to give you an idea of the capacities as a function of diameter and how high they can be held in the air, let's look at the biggest one. So we can achieve a 3 million gallon storage capacity with a tank that's almost 120 feet in diameter, 45 feet tall in the tank part, and stuck 64 feet in the air. So there's a lot of hydraulics as well as structural engineering that goes into these things. This one is either for Plano, Texas, or Plano, the manufacturer of fishing tackle boxes. I don't know which. And here's another one, again, of the spheroid tank. So much of this information for a specific tank would be available on the internet. And if you had a design need, you would hydraulically design it to come up with these required head ranges and required volumes, and then search the internet to find an appropriate vendor, or if you have to custom build, you have to do it. So one of the bigger tank manufacturers in the U.S., I'll make a shameless plug for CB&I, which is also a major contributor to the Department of Civil Engineering here at Texas Tech. They've built tanks like these, and they're big into ground tanks all over the world. So one of our departmental benefactors is very expert on tank building. And although it may seem kind of not very new, there are still tanks that are built today, and this is an ongoing need in civil engineering. And I'm showing this particular picture right here, dated 2014, so it's about 6 years old now. But the tank in the photograph was installed and designed by my wife, so it's still good business. So this is down in Far, Texas. Mexico is less than 2 miles from where the photograph is taken. I can't quite remember what the direction of the photographer is, so I don't know if we're looking in towards the United States or rises in the east, sets in the west. It looks like an afternoon picture. So it could be looking west towards Mexico, as far as right where the Rio Grande bends. A second type of a tank not often thought of are underground tanks. So my comments on that, it's more than just a hole in the ground, although it starts as a hole in the ground. To drain an underground tank, we usually have to use a pump to drain it. The notable exception being in the photograph here. So this is a photograph of an intersection in San Francisco. And I grew up just a little bit beyond that house right there. And so these are called cisterns, and underneath this brick circle is this big metal tank. So let's consider what this tank has to do. It's supposed to be full of water, and this water is intended for firefighting in San Francisco, because there's a lot of hills there, and it's not convenient to pump water up over a hill to fight a fire. They took advantage of the hills. So that it's got to store water, okay, hole in the ground, but it also has to be able to take the traffic loads on top of it. And so for this big hole in the ground, the choice are steel tanks and then a curved arch roof. So when you take your Timoshenko class in structures on shells and shell structures, the shape of this is precisely designed so it transfers the load from the surface outward towards the periphery and sideways into the soil, or the hill as it were. And these tanks don't necessarily need a pump to drain them because they're on hills and there's always a downhill. Another one is shown in this picture, still a hole in the ground. Now this hole in the ground is dug on the surface. It's lined with plastic garbage bags, although it's a very expensive garbage bag because it's intended to hold water, not garbage. And then they put a bunch of old milk crates in there that they get from behind the grocery store. Not really, these are customly engineered milk crates. The purpose of these crates is to have a lot of porosity so water can be stored between them, but also to transfer the surface loads from when this is backfilled down to the soil beneath it. So underground tanks are actually quite complicated engineering structures because of their three roles they have to play: store water, provide enough structural support to hold the overburden up, and have some way to completely drain. In this particular diagram, the complete draining occurs in this cylindrical location. There is a pump vault in there, and a submersible pump would be lowered in there, and you would drain the tank by pumping it out. This particular one, this rain store, is in operation at one of the DART stations, the Dallas Area Rapid Transit, and most of the land beneath that particular station, I don't know where it is anymore, is built with this, and they can store an hour or two of storm flow and delay flooding. So that's an introduction to tanks. Let's move on. So this next section discusses the purpose of storage, the kinds of reservoirs, and calculating. And by kinds, we've actually already seen those. So the first we'll look at is equalizing or operating storage. So this is a type of storage quantity that we design for the purpose of equalizing pumping rate into reservoirs, providing storage for peak demand times, and providing system pressure without booster pumping. And that's because booster pumping is expensive from an energy consideration. So if we can provide system pressure without having to run a booster pump all the time, that's desirable. The second component is the fire and emergency pressures that are required. We obtain those values from our design documents, such as RG 195 in Texas, which states explicitly that the pressure in a distribution system that's also supplying water for firefighting has to be bigger than 25 pounds per square inch. So they put that pressure requirement there actually for two reasons. The first reason is so that there's enough pressure to make the system positive pressure, so that any leaks or breaks in the system won't allow contaminants to be introduced into the distribution system. The second reason is so that the fire department has sufficient suction head for their booster pumps that they use to push water up into burning flames and make them go away. So that the types of reservoirs where these considerations are in surface reservoirs, so those are the big tanks on the ground, standpipes, and elevated tanks. We've already seen pictures of all these. And so here is a diagram that's attempting to depict the 3 storage compartments. There's no real particular order to the diagram. It's just a cake that's made out of a mint layer, and then a blueberry layer, and then a cherry layer. And I've colored the service storage in green, emergency in blue, and fire in red for no particular reason. And as I stated earlier, fire could be part of emergency, but oftentimes they're considered separately because the intent of emergency storage is also to have enough water in reserve for if there's breaks in the system and it comes bubbling out in the street. It takes some time from when there's a water leak to when the citizens call the municipality and tell them they got water bubbling out in the middle of the street to when they can get around to fixing it. So they need to have enough supply to account for that time interval. It can be on the order of a few hours is probably enough, or a few days, and it may be by statute depending on the community. And then fire storage is prescribed by either statute, or if that's not available, you would use the insurance service office's documents. So what's the goal of flow equalization? Flow equalization is sufficient storage to account for peak demands in the system without having to exceed supply capacity. And a desirable volume would be 1 to 2 days of average daily demand. If you recall from the demand lesson, the demand comes at different times of day. And in terms of system design, if we design for average flow, which makes sense, it'd be a couple times a day that we have flow rates much bigger than that average value, and other times a day when it's smaller than that average value. By using storage, we can select a pump to supply the storage reservoir that only has to operate at that average rate. So when the peak demand comes, we draw excess from storage, and when the deficit in demand comes, that's when we're going to refill the storage. It's a lot like a bank account, where one keeps money in the bank for the various expenses that occur during a month. So during high expense times, you're writing a check and your bank account's getting diminished. And during low expense times, hopefully you have income coming in and the bank account replenishes. Unlike bank accounts, water accounts can only go to zero, whereas your bank account can get negative. That's called credit, and that sometimes is a frustrating thing. So a desirable volume that's often used in design, and this isn't prescribed anywhere, this is more of a rule of thumb, would be 1 to 2 days of average daily demand. That should allow one to handle ordinary changes in demand during a day. Then fire storage is sufficient storage to allow the system to meet the routine uses plus a substantial fire flow. And the desirable volume is based on the expected fire flow rates multiplied by a required fire flow duration. And again, depending on application, a lot of that is prescribed. For instance, in large buildings, there's generally tanks on the top of the building whose sole purpose in life is to store water to operate the sprinkler systems. And then depending on how many stories and then what the surface area per story is, the fire marshal in the area that matters has a certain amount of duration, like the sprinklers have to run at 25 psi for 1 hour. And then you multiply that by the number of floors, and that tells you how much volume you have to store. There are similar requirements at larger scales. And then emergency storage is the storage that's provided to allow the system to operate without external supply for a period of time to allow for repairs or other unusual circumstances. If a system doesn't have emergency storage, then every time there's an upset, some kind of failure or break in the system, that will lead to either an interruption of service or a boil water order, which means that the system has been microbiologically compromised and you don't know if the water is safe to drink, so you have to tell all your customers to boil the water. And that's not a good thing. So what we want is those interruptions to be rare. Once every 3, 5, 10 years, something like that. Otherwise, we can maintain the system's operation while we make these repairs or deal with the interruptions. A desirable volume for that is about 1 to 2 days of average daily demand. So keep in mind, emergency and flow equalization, again, both rules of thumb are about the same amount of storage. So one could compute flow equalization and simply double that result, and that might be sufficient for that plus emergency. So the question comes, how much of those in actual volumes? So an engineer would tend to choose for larger volumes because reliability is proportional to how much extra capacity you have available. Economics would argue for the smaller volumes. The person paying for the system says, why am I storing water that I can't run through a meter and recover revenue? And that's a fair argument. As a designer, you have to balance these competing choices. You want to avoid the owner's argument that they don't need any storage and back off on the engineering argument that they need 2 weeks worth of storage, because then nothing will ever fail. There'll be some compromise between the two, and that's done in client management meetings. An additional consideration is how long that water sits in storage before it gets distributed. The residence times in any storage reservoir for treated water should not exceed a reasonable amount of disinfection residual contact time. So if the disinfection method is chlorine-chloramine, the residual will last and be effective for about 6 to 10 days. That's taken out of one of my old environmental engineering books. So we don't want to store water much more than a week ever if we want it to have sufficient disinfection residual to traverse its way through the distribution system to the customer's colons and kidneys. An alternative, of course, would be to treat the water as it leaves the storage facility, but that's an added cost that we don't have to incur if we are fortunate enough to design it right. And we may have to distribute the storage devices throughout the community if it's a big enough community. The hydraulic retention time of any such reservoir should be no longer than 8 days as a reasonable rule of thumb. I would design it for 7. That's 1 week. So if something happens on a Sunday, you have 5 days to deal with something that happens. Or I guess on a Saturday, same thing. For instance, the water treatment plant in Lubbock that takes the water from Lake Allen Henry is actually on automated control during the weekend. There's somebody that can get to it pretty quickly, but pretty much if anything goes wrong and the computer program can't handle it, it's 2 days until they can get around to starting any kind of repair or upset repair. Now they have sufficient water stored there that's not a problem. But those are the kind of things that happen in our more modern systems. Is to save employee money, we have to operate the systems several days in a row unattended. And our computer programs are pretty good. They can handle most things that we can anticipate that would happen. But literally, if a piece of hardware breaks and there's nobody there, all the computer can do is either do an elegant shutdown and report that a piece of hardware is broken, and you have to get a crew out there. And if that comes in on a Saturday afternoon, you would ask, how much storage do I have? Because that means you could schedule the Monday crew that's going to go there anyway and not have to incur overtime costs. So what's hydraulic retention time? Hydraulic retention time is defined as the ratio of storage volume to average discharge through the reservoir. And the formula here shows it as HRT is equal to the volume of the tank divided by the flow through the tank. And if you recall that volume is going to be length cubed and flow is going to be length cubed divided by time, the ratio of the volume to the flow rate returns a value of time. So it would be something like hours or days depending on the flow units, the time units used for the flow. That's not the whole story if the tank is a reactor, because we would have to worry about the corners, but for just an average how long material spends in the tank, this is a good starting point. So how would we come up with some of these operating storage? Well, here's a classic method for coming up with flow equalization storage. In bullet items, it doesn't look too hard, and I'll show you in pictures in a second. So we would determine the hourly demand for a design day. We would then calculate the cumulative draft for that day, which is to take each of those hour demands and add them to each other until we accumulate the whole day's worth of demand. And then plot the cumulative draft versus time, usually on a 24-hour plot. And that represents our demand situation, or what our system requires from us to operate as designed. Then we could draw a diagonal line representing constant pumping for the 24 hours, and we could determine the required storage as the sum of the two maximum ordinates. Now let's look at that in pictures. So here's the same statement in pictures. So this curve here that the cursor is tracing represents the cumulative demand as a function of the 24-hour cycle. And so here at midnight, there's a certain demand and it accumulates. And then around 6 a.m., the slope changes and it accumulates more at a different rate. And then we get around 8 p.m. and it starts to flatten out again. And then it would repeat the cycle the next day. So one thing we could do is just pump in water at whatever the indicated slopes are all the time and just boost water into the system. No storage required. But first we'd have a pump running all the time. It would run at very low flow rates until the slope changes, and then it would have to run at a higher flow rate and then slow down again. So mechanical devices, like pumps and their electrical motors, don't work well if you change their speeds a lot. I mean, they can be made to work, but every time you change speed, you're changing the forces on the bearings and the lubrication system. Pumps run better at a constant speed. So let's suppose we had a pump that runs at the flow rate indicated by this dashed line. It's labeled as the supply line right here. There's two periods in this, comparing the two curves, location 1 and location 2, where the distance between the supply line and the demand line are the biggest. In this case, supply is greater than demand, so you would be adding to storage here. In this case, demand is greater than supply. And so the usual method is to find the biggest deviation below the supply line and the biggest deviation above the supply line, add those two together, and that gives us the required storage. And under those conditions, the storage will will take up the cases when the demand is greater than supply. That's if we're running the pump 24 hours a day. Let's suppose we only ran it 12 hours a day from 6 a.m. to 6 p.m. Then the supply line would go from 6 to 6. It would be a line right there where the cursor is going back and forth. Here's that same example. And in this case, we find the maximum deviation at the two locations, add them together, and that would be the desired storage. And so during the periods when the pump's not running, all the demand is being satisfied by drawing down water in the reservoir. Oh, cat, just change the volume. Well, you can stay there. You're fine. This is perfect. You're helping me. In this case, when the pump is not running, all the demand is satisfied by water coming from storage. And then when we turn the pump on, we replenish that storage. And we won't be replenishing in this region. We'll still be drawing from storage until we get crossover. And then up here, we're starting to replenish the storage. And you add the two together, and that's the required storage. So here's those same information shown in a spreadsheet. We'll actually look at this, this particular spreadsheet shortly. And so what we have is average hourly demands in the table below, and we want to find the uniform pumping rate and the required storage. So we have the times listed here. We have the hourly demand, which is determined either from historical records or similar communities nearby, or a demand calculation like you're doing for exercise 3, multiplied by a hourly variation chart taken from some reference. And from that we accumulate the required volumes. In this third column, cumulative demand in gallons. And then we pretend we have a pump. If we have a pump running at 5,110 gallons per minute, it's supplying these particular volumes. So in the early part, the pump is supplying more water than being used. And then at crossover, the opposite is true. There's more water taken from storage than being added to storage. We look through these differences and we find the two biggest ones, the biggest positive one and the biggest negative one. We use the absolute value of the biggest negative one. We add the two together to get, in this example, 1.3 million gallons for this situation here. And a 1.3 million gallon tank pretty much guarantees that we can satisfy the flow equalization demand at all times. You notice the only time it drops to 0 is when it gets to the end and restarts the cycle. If we play the same game for a 12-hour period, depending on where we start and stop the 12 hours, here we find the biggest negative difference and the biggest positive difference, and we add them together, the absolute value of them, to come up with a 2.7 million gallon is required if we only have 12 hours a day of pumping. And if we have shorter and shorter pumping intervals, then those would change. The reason to consider less than 24 hours is not everywhere in the world do you have electricity 24 hours a day. I've personally visited places where the electricity is on for only portions of the day, so you would want to leverage that. Or if you are designing for a case where you might lose power and have to provide your own, then you may only have enough diesel fuel stored to run your generators for 12 hours. That completely defines your storage requirement. And depending on when that 12 hours occurs, the required storage values might be different. So in this particular case, if it starts at midnight and pumps to noon, this one has a much different storage requirement than the prior one, from 2.7 million to 4.6 million. So the prudent designer would have to check several of these in order to specify an appropriate volume for storage design. So in doing these, you have to decide which demand we're going to use, whether we're going to use daily or peak. And these volumes are added to emergency and fire flow. Ultimately, it determines the tank volume that's required. And then once we know the tank volume that we want, which would be the biggest of all the anticipated volumes that we examine, then we could choose a tank type. Elevated, at grade, buried, and that decision in turn determines the shape, the elevation, the diameter, and the minimum and maximum level. In the case of elevated tanks, we also have substantial structural considerations that are outside the scope of this class, but your structural engineering classes cover that. Keeping in mind that most elevated tanks are a large mass on top of a relatively slender object, and so there's a certain required stiffness for it to work correctly. And I forget if there actually is a part 3. Oh, we'll get to part 3 in a second. Let's go look at the so here's the storage examples that were used in making the presentation. And so this could be a typical homework or exam type problem. The average hourly demand rates in gallons per minute for a municipal system are given in the table below. So midnight to midnight. The average daily demand starts at 0 and ends at 1278. So you could argue that 1278 and 0 are the same place. And find the uniform pumping rate and required storage volume. And then repeat it for 6 a.m. to 6 p.m. and 6 p.m. to 6 a.m. So there's a problem statement, and let's go look at it solved in the spreadsheet. So I hope this works. I actually never tried to run the spreadsheet over the spinning beach ball is often a good thing. That looks correct. Okay, that should be big enough to see. So here's the first part. Here's that hourly demand going from 0 to 24 hours. And this is taken directly from that table that was in the problem statement. Here's the cumulative demand, and let's look at the formula right here. The cumulative demand says, look at the current hourly demand in gallons per minute. In this case, multiply by 60 to turn it into gallons per minute times 60 minutes is how many gallons it needed in 1 hour. And then add that to the previous cumulative amount. So it says this is equals above plus 60 times left. And so at the end of that hour, at 1 a.m., to satisfy the stated demand, we would have had to supply 71,100 gallons. At 2 a.m., at the end of 2 a.m., we would have had to supply the 71,100 gallons plus almost another 70,000 gallons for a total of 138,660 gallons. At the end of the third hour, we take the 138,660 gallons and supply about an additional 60,000 for a total of 187,980 gallons. And we repeat those calculations all the way down. And at the end of the 24-hour period, we would have had to supply a total of 3,679,000 560 gallons. Now the uniform supply, this spreadsheet's already built, so it's 2555. Let's suppose we bought a 200 gallon per minute pump. We'd see at the end of 24 hours, the most it could produce is 288,000. So if we buy 400 gallons per minute, we get 500,000. 800, we're up over 1 million, but we need almost 4 million. So 5,000 gallons per minute, we don't need that much. There, we're getting close. At 2,500 gallons per minute, we're pretty close. So 3.6 million pumping, 3.67 million required. And I remember it was 255. I think that was the number that was there. And we can use a interesting tool. We can use GoalSeek to get the correct number. So let me see if I can find it. GoalSeek. There we go. Now let me go ahead and do that. Tools, GoalSeek, set cell equal to 0 by changing cell. Hit the okie dokie. And we're done. So now we've got the constant pumping rate will provide at the end of the day the total required demand. Now let's just copy this formula so we're going to do, I'm doing demand minus supply. And so here we have our biggest negative deficit is right there, and our biggest positive deficit is right there. And in this case, it's actually already taken care of by the spreadsheet. So what the spreadsheet's doing is it's finding that number and that number automatically, algebraically adding them together. In this case, it takes care of the minus sign for a total required storage volume of 600,000 gallons. So that's all that's needed if we have 24 hours to pump. Now the second part of the problem says, what happens if it's only going to pump from 6 a.m. to 6 p.m.? In that case, we have a much shorter time interval to consider. And let me copy the calculation. This is automated already. Let me check that this. And so in this case, we have to get that number and that number to equal one another. So we adjust our flow rate by that. So now we need 5,110.5 gallons per minute. and then the spreadsheet automatically finds the maximum and min values of the deviation column, adds them together to tell us that we need 1.3 million under this condition. And then the last one, 6 a.m. to 6 p.m. and then 6 p.m. to 6 a.m. Okay, so this is not at 6 p.m. to 6 a.m. yet. So what we would have to do for that is actually find the time. Let's grab all that since the work has been done for us. Good. Okay, so it's searching the right ranges, and this we don't know yet. So let's see, 6 a.m. to 6 p.m., then we need to go 6 p.m. Oh, it's been reorganized here. And so here we would start, again, guessing the required flow rate until that number and that number equal each other. And lastly, we need to copy the logic. Let the computer find the required storage, 2.3 million gallons. So with the time and the hourly demand, the computation of equalization storage is relatively straightforward. And nothing in the spreadsheet, there's nothing that special about it. You could just as easily do this with a hand calculator. Maybe not just as easily, but essentially with a hand calculator. Didn't want that to happen. Let's see what happened to, that was weird. And now to finish the lesson. So we're not doing computer models today, but storage in computer models is initially confusing. Once you see some drawings that I'm about to show you, I think it makes it quite a bit simpler. So the two computer models we'll use this class are quite similar to, computationally, they are the computation engine of commercial programs, but the commercial ones have more extensive interfaces. So both EQUALIZATION and SWIM share some similar features in storage requirements. The minimum data that either of them is going to require is we have to identify the bottom elevation of the tank, the minimum pool elevation, so that's the distance above the bottom elevation to where the lowest part of the pool is going to be. The beginning pool elevation, that can just as well be the minimum as the maximum. The maximum pool elevation, which is how deep the water can get in the tank. And either the tank dimensions or a depth storage curve. So this graphic is illustrating a way it would be conceptualized in EQUALIZATION, and it would be quite similar for SWIM. Suppose we have a node that's connected to our water distribution network, and also connected to that node is an elevated storage tank. In the case of EQUALIZATION, as a for example, that tank is connected by a pipe element or a conduit element, and we have to tell it how long that conduit element is. And the length has to make sense. In this particular example, there's 180 feet of horizontal and 120 foot of vertical. the minimum length this pipe could be would be the 120 foot of vertical. If it's less than that, the computer program would identify that as a nonsensical length based on the minimum pool elevation supplied for the tank. Then we provide the bottom elevation of the tank, which gets assigned to the node. Then from the bottom elevation to the minimum level is supplied in the tank input information, and then the min level to the maximum level is supplied as a tank information, and then we either supply the diameter or a storage depth curve. And we can also use volume versus depth to convey the storage. So when we get to the computer programming in a few more meetings, keep in mind this graphic, because it will be very helpful to you in how to conceptualize elevated storage tanks or storage tanks in general into a computer model. And even the models that we're going to build ourselves by hand, just to know how, we have the same mental construct. So I think it was a short lesson today. That's all I had planned for today. And let's address the exercise 3 question on fire flow to be sure I'm not lying to you too badly. And wait for Blackboard to generate revenue. There we go. So here's our network, and it says we want to get the fire demand. And we were explicitly recommended to use the San Marcos manual, which wouldn't kill us if I go to the right lesson, would it? There we go. And we just read through the manual and see what it says about fires. Nothing on fires on that page. Nothing fires on that page, although it's pretty handy. It's telling us what Hayes and Williams coefficients to use. That's pretty handy. And it has conversions for service unit equivalents. Tells us what fire hydrant has to be, ductile iron. So it tells us fire hydrants are installed at the intersection of a cul-de-sac and connecting street, and fire hydrant spacing is in a different section. So we'll get to that shortly. This is supposed to be section 110. Fire hydrants shall be located as near to street intersections as possible, but out of the radius of curb turnouts. And in single-family residential, fire hydrants every 500 feet. So that gives us all the information we need. There's going to be a fire hydrant at every cul-de-sac entrance, regardless, and then a fire hydrant every 500 feet. So when we return to our picture, we're going to figure out fire hydrants. So 500 feet is roughly half of the 1100. So first we find the cul-de-sacs. Here's a cul-de-sac, so there's going to be a fire hydrant there. That distance is longer than 500 feet, so there'll be a fire hydrant there, and there'll be one somewhere in here. And then we just do that for the other cul-de-sacs. So there'll be 2 on that one, 2 on that one. The rest are through streets. And then I would say going from these intersections, work 500 feet to get the number of hydrants along that street, 500 feet along that street, 500 feet along that street, and then 500 along each of these. And then repeat that, and that would give you the total number of fire hydrants that are required in this subdivision. And there should be a flow specification for each fire hydrant. So I think it's probably 1,000 gallons a minute would be my guess. So first you locate the fire hydrants, and then we're going to go ahead and specify their flow rates. Hydrant flow. That's an excellent question, Yuan. You would, one would make a determination how many hydrants would be in use during any fire. It's certainly not going to be all of them. So maybe 2 or, well, actually 2 hydrants at most is most likely. Yeah, I think it explains in the table I passed to someone. But to answer the question, you would not, let's say you identified that you got 18 hydrants in that particular thing. You would not have 18,000 gallons per minute fire flow for the whole subdivision because it's unlikely the whole thing's on fire at once, unless it's out in the West Coast right now. But with the minimum spacing of 500 feet, most fire trucks really don't have more than 250 feet of fire hose. So the most number of hydrants that you could involve in a 2 or 3 alarm fire would be 2, and that's only going to get you partly close to the fire. So I would say with that you would at most only have 2 hydrants involved in any fire at once, and so you would design it for 2,000 gallons per minute total fire flow for the system. And you would state that in your design documents, that during the fire flow calculations we assumed that at most only 2 hydrants could be in service because of practical limitations on the carrying of fire hose by the fire department. And the amount of hose that a fire department has is usually specified somewhere. So I hope that gives you both guidance to complete the exercise and some of the art involved in water system design. It's those kinds of thinkings that has to be incorporated in the design because it's not explicit. They also tell us how long we have to provide that. 2 hours in the case of the San Marcos guidance document, which is what I would like you to use for this exercise. So that's my, I wouldn't call that a hint, that's my guidance to you for completing the exercise. Oh, I regret that. I shouldn't have done that. Let me get back to, I don't want to lose the link to the, oh, Blackboard's running awful slow today. There we go, back to lesson 7, and more important, I just want to get back to the link. Okay. Are there any other questions? Otherwise, I'm going to go ahead and have this as a short day and thank everyone for their attention and patience. And next time, we'll start looking at distribution networks. So the next few lessons are complex, and I will try to go as slow as I can. I have a tendency to just blow through stuff, but we're going to actually look at the arithmetic of network systems analysis from the standpoint of if we had to do it in a spreadsheet, for instance, and then we will go into the professional software. And after we've done if you're going to do it in a spreadsheet, you should have a pretty good understanding of what goes on under the hood in professional software. And the advantage of that is it's quite easy to put numbers into the professional software and get something to run and get pretty pictures out. Sometimes output doesn't make sense, and oftentimes it's usually a hydraulic input error. If you know how it's doing the computations, you can run those errors down pretty quickly and find a conceptualization error. I mean, it's literally as simple as a decimal point in the wrong place. So that's where we're headed over the next few lessons. And there's a few more quizzes that are already prepared and queued up, but they haven't been activated yet. And at some point in the next few weeks, there'll be an exam, but it's going to be entirely take-home. And you can think of it as somewhat of an extended quiz or extended homework assignment. So I will, I'll give you a fair warning on that, and probably a week to do it. And then we'll continue from that. So if there's no further questions, I'm going to go ahead and terminate the call today. Again, thank you very much. Have a great afternoon, and take care of yourselves. Wear your mask. Try not to breathe on each other. All the usual warnings in today's day and age. Okay, goodbye. Stop the sharing. Terminate the call.